qualche minuto. Sempre di più. Allora, ecco bene.
Hello.
Hello. No. Okay. Okay, can you hear me?
Yes.
Okay. Too much high. Now?
Yes.
Yes.
Yeah. Okay, perfect. Now, just a moment that I connect my iPad and we will start. Okay. Okay. Now, we left with this circuit during the last lesson. That was this circuit. A JK circuit with a clear signal and with a D register here, that is this one. Okay, both are derived from the SR, but in particular this is true because as you remember, the SR is the main implementation of a bistable circuit, or if you want, the simplest implementation of a bistable circuit, with the possibility to read and to write by using set and reset signals. No? As you know, just for a brief recap, here we have that this is a bistable circuit that implements a circuit that is capable to store a bit depending on its state. So a state that is associated with a 0 or with a 1. But this implementation cannot be written. I cannot change the value that is stored in this bistable circuit. So the alternative is the implementation by using this circuit here. Okay, S, R, so we have not Q and Q. By using S and R, I can change the value that is stored here. S, R, Q, obviously not Q, 0, 0, 0, 1, 1, 0, 1, 1, and so we have that Q, not Q, 0, 1, we have 0, 1, 1, and 0 at invalid state. Okay, so starting from this circuit, and by using also its equivalent implementation by using NAND gates, this implementation use the NOR, but if you want, we can change very easily the implementation of this NOR by using NAND, for example, by using Pasching bubble, for example. No? So, for example, here you can add a bubble here and a bubble here, but a bubble here means that I have to change these. Okay. A bubble here and a bubble here, but a bubble here nullify this one. This bubble nullify this one. I can add a bubble here, but I have to negate this one. A bubble here, but I have to negate this one. And a bubble here, and a bubble here, and these two bubbles nullify. So I have this situation. This situation is that I have an OR with two bubbles at the input, another OR with other two bubbles here. I have a not S here. I have a not R here, and I have a feedback connection here and another feedback connection here. So this is not Q, this is Q. Okay, then at this point I can use the Pasching bubble applied to these two OR, having the negative input. These two gates are transformed into NAND gate. So this circuit comes this one, not S, not R. Oh, sorry. And okay, and if you want here, not S and not R must be implemented by using inverters, not gates, as S and R. Okay. So this is the implementation that we saw during the last lessons. This circuit can be complicated if you want, not if you want, but usually they are complicated by the addition of two more signals that are not just only a clear, but in general it is provided with two more inputs, that is a clear and also a preset. For example, a JK implementation with a preset and a clear assumes this form. As you remember, the JK is composed by using 4 NAND gates. These NAND gates continue to be used also in this case, but all the NAND in this case becomes 3 input NANDs. 1, 2, and 3. Okay, so at this point we have that one input here is for this one input here is for this one. Oops. Okay. Another input is for the feedback, obviously for the bistable implementation. Okay. Then we have that if it is Q, this is not Q, here we'll have key. Okay, here we have J. Okay, then we have a Q that is feedback in here. And then we have a not Q that is feedback here. Okay, at this point we have to add 2 more signals. And Claire?
May I ask a question?
Yes.
The sequence of, I mean, we wrote not Q before and Q below before, but now we wrote Q upside and not Q downside. Is it important?
The position of a Q and not Q?
Yes, yes.
It's important since we the scheme, the usual behavior of this JK is that when J is equal to 1 and K is equal to 0, we want that the output is equal to 1.
Okay, thank you.
That means that if I look here, I want that this is 1 and this is 0. And it's important for this reason.
Okay.
Then I want to add Claire. The Claire just operates here and here. Here and here. this is a, oops, this is an active low clear signal. And in the same way, I have also a preset here and here, just for a sort of symmetry. Okay, this one and this one, and this also is a preset, an active low preset. Active low means that preset and clear must be 0, not preset and clear, but these two inputs must be 0 to operate. Okay, and indeed, for example, here, if I put clear at 0, if this clear becomes 0, this means that this signal will be 0. The 0 at this input just put the output of this NAND to 1, this to 1, then this clear here at 0, put this output to 1, okay, and this means that the output here, if this is 1, this is 1, so I will have 1 here, 1 here, and the preset must be 1 to be deactivated. So at the input of this NAND here, I will have 1, 1, 1, and so the output will be 0. Okay, so when clear is 0, the output will be 0, namely Q0 and not Q1. Okay, I will use this one. Okay, this 0 impose this suddenly this not Q to 1, then impose the output of the first NAND here to 1, and considering that the feedback here will be 1 from not Q and 1 from the fact that preset must be 1 because preset and clear cannot be both activated. So if clear is activated being 0, preset must be necessarily 1. This means that the input to this NAND are equal to 1 and the output will be 0. Okay? So on the contrary, if I put this to 1, so it is deactivated, and preset to 0, I will have 0, and the preset 0 means that here I have 0. Regardless of the other input, the output here will be 1, so Q becomes 1. The feedback signal here will be 1. Clear here is 1. A preset equal to 0 here means that regardless of the value of K, the output of this NAND will be 1. So the input of this NAND will be 1, 1, 1, and the output, not Q, will be 0. Okay, so when preset is activated, namely when it is equal to 0, the output becomes 1. If clear, regardless of J and K. If in turn preset is equal to 1, so it is deactivated and clear is equal to 0, then the output will be 0 regardless of J and K. Obviously, if both clear and preset are equal to 1, are equal to 1, then both are deactivated, and so this circuit behaves like a common JK flip-flop. Okay, so I have the two command signals J and K that are used to write a 1 or write a 0 during normal operations. Clear and preset can be, for example, activated by a control logic that want to reset or want to set the state, the value that is stored in all the flip-flop, and so these two signals can operate, for example, to initialize the elaboration. Imagine that I'm starting the elaboration, and I want to be sure that all the content, all the bits stored in the flip-flops are equal to 0, so all flip-flops are reset, and so a control logic could activate the clear signal in order to cancel all the values of the flip-flop. Okay, so that's the motivation of this circuit. Okay, now obviously this clear and preset can also be used with, for example, with D flip-flops. So I invite you to define a D flip-flop provided with a clear and a preset. It is very, very, very simple to build. You have just to remember how the JK has been derived from the SR and how D is derived from the SR. Remember that D is essentially an SR where the set is connected, is put in relationship with the reset by using this knot, and so the implementation of a clear or a preset here is very, very simple. Okay? Okay?
Okay.
Okay. Obviously, try to implement. But then, obviously, we can discuss together if you have some problem, and if you could ask for explanations and so on. Okay, now, go ahead. Now, at this point, we have to introduce another input signal. It is an important signal since it is an enabling signal. Enabling signal that means that if this enable signal is low, the flip-flop does not operate. If the enable is high, this flip-flop operates. It is a very important signal because the ability for this flip-flop to be activated or deactivated by this enable signal allows the introduction of a control logic, and in particular allows the possibility for this flip-flop to operate like a synchronizer, like a circuit that introduce a time base, introduce the time variable in the equation of Boolean algebra. Now, starting with the SR, but if you want, we can do it with a D flip-flop, for example. The introduction of an enable signal is very easy because in such a way it remembers the JK construction. So, remembering that, for example, the SR has been implemented by using NAND gates in this way, we have a bistable circuit that is built by using a two-input NAND and obviously we have to add a feedback network here and the feedback network here. Now here we have Q and here we have not Q. Okay, now we need to introduce a third signal. A normal SR just requires of two more inputs, S and R. Now S and R fulfill all the inputs of these two NAND gates. In order to add a third signal, I need to add at least another gate. But since this enabling signal must be in relationship with the S, with both S and R, we need to add two more gates, two more NAND gates. So one gate here, and one gate here. Here we have set. Here we have reset, S and R, and then here we have an enabling signal. Operations of these enable signals are very easy, because if you consider that this enable is 0, okay, if it's 0, the output of these two NAND, of this NAND 1 and NAND 2, will be always equal to 1, regardless of the value of set and reset. Is it clear to you? If here
Yes.
set is equal to 1 and is equal to 1, the output will be always 1. And the same happens if this, for example, will be 0, the output is always 1. Okay, now if here we have 1 at the input of this second part, now what happens? Imagine, for example, that the previous value of Q and not Q are 1 and 0. What happens is that 1 feedbacks here, so here we have 1, but 1 here, the output continues to be 0. 0 is feedback here, 1, 0, the output continues to be 1. On the contrary, imagine that, for example, here we have initially 0 and 1, then this 1 is feedback here, 1, 1, the output continues to be 0, 0 is feedback here, 0, 0, 1, the output continues to be 1. So it means that if the if this enable is equal to 0, the output continues to be the previous output, the previous, namely this regardless of the value of set and reset, the output are stable at 0 or at 1. So it means that if enable is equal to 0, the output cannot change. The output cannot change, and means that the this flip-flop is in an hold state. When enable is equal to 0, the flip-flop is in a hold state. Hold state, it means that, I repeat, that even if I change the value of set or the value of reset, these two values have no effect on Q and not Q. And the flip-flop, in particular this feedback here, continues to be in the same stable state that it in which he has been carried when enable is equal to 1. And indeed, if I change the value of this enable, and now I put this enable to 1, okay, at this point this circuit continues, starts to be dependent from the value of set and reset, so it starts to operate normally. So, for example, at this point, just to give you an example of operations, if enable is 1, supposing that the previous value was 0 here and 1 here. Now, if enable is equal to 1, suppose that set becomes 1 and reset becomes 0. Then, here at the output of this first of the NAND 1 will have 1, 1, so the output is 0. The output of the second NAND here 1, 0 at the input, the output is 1. Okay, so here, sorry, I have to complete it. Okay, so the input, the output of the, naming this as 3 and 4, the output of the NAND 3 is, regardless of the second input, regardless of this input here, is certainly equal to 1, because I need just of one only input that is equal to 0 to determine the output. So this means that Q switches to 1. Now this 1 is feedback here at the input of the NAND 4. Both inputs of this NAND are equal to 1, so the output will be certainly equal to 0. So this not Q switches to 0. And that means that set and reset are correctly operating. Obviously, the same thing happens if we put set to 0 and reset to 1. In this case, we have that Q becomes 0 and not Q1. Okay, so the effect of this enable is that to put this circuit in a hold state, in a retention state, where the state is preserved regardless of the inputs. Okay, this is a very important operation. Someone names the complementary state of the hold as transparent. Namely, it means that if the enable is low, nothing can change the state of this circuit. So it is named as hold. If enable is equal to 1, this circuit is transparent to the effect of the set and reset signals. Okay, this behavior is much more evident if we consider the D flip-flop with an enable signal, obviously, of course. For example, the D flip-flop with enable here we have one input, one other input. I can duplicate this one. I can duplicate this other one and duplicate this other one. Okay, now input here, input here. Here, here. Okay, so I have Q, not Q. Okay, then remember that the only one input is D, and D is in relationship with the other input with a negation here. Okay, so this one, oops, this one, and this one. Okay, the enable operates as input of these two NANDs. And so here we have the enable. Now, operations of the circuit are very, very similar, quite the same of the S and R of this one, of this circuit. They are very, very similar. It is enough that you consider that if D is equal to 1, is the same behavior of having set equals to 1 and reset equal to 0. And on the contrary, if D is equal to 0, it's the same behavior of having set equal to 0 and reset equal to 1. So the behavior is absolutely the same. However, just to give a more intuitive explanation, now if enable here is equal to 0, okay, if enable is equal to 0, for the same motivation that we saw with the S and R enabled flip-flop, here we have that this D flip-flop is in an hold state. I want to write it here. Okay, so regardless of the value of D, Q and not Q cannot change. On the contrary, if enable is switched to 1, okay, now if enable is switched to 1, if D is equal to 1, we have that the output is 1. So Q is 1 and not Q is 0. On the contrary, if D is equal to 0, we have that not Q is equal to 1 and Q is equal to 0. So it means that the behavior is like if when enable is equal to 1, this circuit behaves like if it is transparent to the value that D assumes. So if D is equal to 0, the output becomes 0. If D is equal to 1, the output becomes 1. By looking at this behavior, the opposite, the complementary state to hold, is called transparent. Okay? Is it clear to you?
Yes.
Okay. Remember that even if I add the enabling signal, just to simplify the circuit, I avoided to use also a clear and a preset. But remember that you could add to this both S, R, and D with the enable. You could add also a clear and a preset in exactly the same way as we done here. You obviously need to modify this NAND by using 3 input NAND and by using clear and preset like I showed previously. Okay. Now, just to complete, obviously we saw the S, R, the D. Just to complete, we could have a look also to the JK flip-flop with the enabling signal. And essentially we have to copy the same circuit here. We have just to modify obviously we need to add 2 this N must be 3 input NAND. So here we have the J input. On this other side we have the K input. Then we have the feedback of Q. Then the feedback of not Q. And then we can use the third input here to add the enable. If you want now, we can. Okay. Here we have the enable. Okay.
Yes.
Operations are essentially similar for the 3 circuits, and clearly the topology is quite the same, so operations continue to be the same. Now, at this point, since we have a signal, an enabling signal, At this point, I presume that we can have just 5 minutes of rest. Okay. I have to introduce now the clock signal, so the synchronicity, and so I need to change the subtopic. Some minutes of rest.
Okay.
Okay.
Hello? Are you there? Can you hear me?
Yeah.
Okay.
Yeah. Hi.
Perfect. Okay. Now, as I said, we have to consider the use of this enable signal from another point of view. Imagine that this signal is not a signal that is normally controlled by a logic. For example, one could imagine that I have a control logic that if I want that this latch operates, I enable it, on the contrary, I will disable. Now, imagine that, for example, this enable signal is a periodic signal. So imagine, for example, that this enable is a signal that is done like in this way. And so on. Imagine that it is virtually infinity. Okay. Now, you can see at this point that it is a square wave, but it is a square wave since it is implementing a 0 and a 1. So it continuously switches between 0 and 1, 0 and 1, 0 and 1. Okay? Now, this means that the circuit now operates continuously switches between these two states, hold and transparent, hold and transparent. So here is hold, transparent, hold, transparent, hold, transparent, and so on. Okay? So at this point, I imagine that you could identify a sort of periodicity that becomes a sort of synchronicity. In what kind? Imagine, for example, now that you have a logic, a combinatorial logic that is using this circuit. Now, in order to make this, consider, in order to simplify this scheme, consider the usual symbols that we use for these flip-flops. For example, for this D flip-flop, for this one, we usually use a very simple symbol. It is a rectangle. Here we report D. Here we report the enable signal. So I repeat here D, Q, not Q, and eventually, if they are if they are present, also a preset and a clear. Bubbles here means that preset and clear are active low. They operates when they are 0. Okay, now if we use this symbol, this for the moment, name this input with N. I've written enable upside of the symbol because in this case enable when it is a periodic signal, enable is not its real name. Now, imagine now, for example, that you have a very simple network, combinatorial network, but it could be also a very complex one. But for example, imagine that you have a network like this. I don't know, and suppose that here you have a NOT. Suppose that the output of this end will be an OR. Okay, so imagine here that you have an input A, here you have a second input B, and here you have a third input C. Okay, consider, for example, this combinatorial logic. F is the output. Now, F is normally sorry, we usually use the Y, we could continue to use this one. It is not important, but just to preserve the same notations. We have that Y is a function f of A, B, and C, where f is a Boolean function, so it is a combinatorial function. Namely, if I change the value of A, B, and C, then the output Y suddenly after a delay, but it changes depending on the actual values of A, B, and C. Now, imagine now at this point that A, B, and C are stored in D flip-flops. So imagine that I modify this circuit so that it assumes this aspect. For example, here, oops. Okay. So imagine here I have A, here I have B, and here I have C. And now, obviously, this other input will be the enable and also imagine that the output is stored here, where the enable signal is the same for all the flip-flops. Now, consider now that this enable signal is periodic, so it is like this one. Okay. Now, what happens in the circuit now? It happens that when enable is low, here, for example, at the beginning, here, for example, or here, for example, or once again here, we have that if A and B change, they have no effects on the output Y. Okay, because, for example, if we name this as A with apex, B apex, C with apex, A first, B first, and C first here don't change if these flip-flops are in a hold state, regardless of the value of A, B, and C. So imagine that A, B, and C could change casually. If the enable is equal to 0, A first, B first, and C first do not change, and that means that Y here doesn't change, and obviously never the output of the flip-flop, we can call it here Y first, and the output as with Y. So Y first and Y do not change. On the contrary, if we are here, when the enable is 1, so these latches are transparent, that means that A first, B first, and C first assume the same value of A, B, and C, and at this point, this combinatorial circuit can operate on the new values of A first, B first, and C first, and so Y first could change. Okay? Obviously, Y, the output here, will change only if when Y first has changed, this last flip-flop is in a transparent state. If Y first change, but this last flip-flop is in a hold state, Y does not change. So, by looking at this behavior and by looking at the fact that this signal enable is periodic, this signal introduces a sort of periodicity also on the elaboration of the input signals, in this case A, B, and C, but you can easily imagine that the same discussion can be extended or can be applied to all the combinatorial circuit. So I'm introducing a sort of periodicity on the elaboration of this circuit. This circuit here, that is normally only a combinatorial circuit, now is operating by following the periodicity of this enabling signal. The signal so operate like a sort of time-based signal, a signal that says when, okay, when, not what, but when the circuit here, this circuit can operate. So this signal introduce the time variable, and for this reason, this kind of signal is not usually named enable, but it has a much more famous name, that is clock. Okay. So just to give a very rough explanation, or if you want a very rough digression about this name, when you say that the processor of your computer goes at 3 gigahertz, for example, you are simply saying that you have a clock signal whose frequency is 3 gigahertz. So you are simply saying that your circuit, your processor, is working with a periodicity of a period. This is obviously a period T. Your circuit is working with a periodicity T, where obviously you know that the frequency is the reciprocal of the period of this square wave. I plotted this square wave by using a semi-period here, assigning a semi-period to value 1 and a semi-period to 0. So 1 and 0 have the same duration. This is normally named as a duty cycle. Duty cycle. The duty cycle is a percentage value, and is in particular the percentage value of the ratio between the T1 or T total in percent, where T1 is the portion of the circuit where of the waveform here, where it assumes value equal to 1, and T total represents the total period, what I named here as total. So I want to indicate this quantity on the waveform, the shape of the waveform. Here we have that this is T1, and this one is T total. Okay, so if T1 is equal to T total divided by 2, it means that the duty cycle, DC for friends, is equal to 50%. Okay, so a square wave having a duty cycle of 50% means that we have this square wave. Usually the clock signal is implemented with the duty cycle of 50%, but it is not mandatory. We could have, for example, a square wave having this shape, here. So the square wave, if the square wave have this shape, it means that we have that T1 and T total are in a ratio of T1 on T total. Sorry, yeah. The ratio is 1 on 4. So we have a duty cycle equal to 25%. Okay? Is it clear to you?
Yes.
Okay. Now, at this point, we have a problem. What's the problem? The problem is that this clock signal that I introduced had a sort of a periodicity on the operation of these circuits here. However, periodicity is not I cannot strictly speak of a periodicity because if these flip-flops here are all transparent, then the output A first, B first, and C first here suddenly change when A, B, and C change. This means that when we are when the clock here is equal to 0, we are in a hold state, and okay, the circuit does not operate. Perfect. But when we are transparent, we have that if A, B, and C change, and imagine that they could change more than one time. For example, we can have that A switches to 1, then switches to 0, and once again to 1. Okay? All the switches when we are in a transparent mode, and then we have that the output, for example, Y in this case, could change more than one time. Okay, so we have a semi-period hold when circuit preserve its previous state, but when it is transparent, this state is no more preserved. So this periodicity is not so good. We have to improve this behavior if we want an actual periodicity. One of the solutions could be, for example, that of reducing the duty cycle. For example, one of the solutions could be that of implement a duty cycle like this, because a duty cycle like this means that the circuit here, the flip-flops are transparent for a very short interval of time. Okay, so if A, B, and C change, we could suppose that A, B, and C could change just one time in this very short period of T1, and this means that probably Y first will change just one time. And so that means that we have one change of Y of the output for each period of the clock signal. This is not a good solution, however, because the duration of this T1, the value of T1 is very, very strongly dependent on the kind of the circuit here, because imagine that you have the delay of the single gates, and these once A, B, and C have changed, we need of time to change A first, B first, C first, and then to obtain the new value of Y first. But these times strongly depend on the configuration of the circuit. If here I have a very complex circuit, or for example I have a lot of NAND having more than 2 inputs, 4 inputs, 5 inputs, and so on, imagine that this circuit is much more slow than the one that I have plotted here. Okay, So imagine that this time is strongly different and depends on the situation. Okay, but so it is not possible for me that I have to adjust T1 for each circuit. For this reason, I have to introduce another solution in order to make that this flip-flop introduce just or enables just one change of the values for each period of the clock. So I want an actual periodicity. In order to do so, these flip-flops here with the enable are not the best solution. In order to improve this behavior, one of the first alternative solutions was the introduction of a master-slave configuration. What is a master-slave configuration? The master-slave configuration is something that can be plotted like this one. Imagine, for example, here that you have a D flip-flop. Okay. I want to use the symbol. So you have D, Q, not Q. Now on the symbol here, we have that the input having this small triangle is the clock input. Now here I have the input D. Okay. The data. Now I add a second flip-flop here. I connect the two flip-flops so that they are in series. So the output Q of the first flip-flop is the input of the second one, but they work with a complementary clock signal. Q and not Q. Okay, so this means that when clock is equal to 1, we have that the first flip-flop receive a clock equal to 0, and the second one a clock that is equal to 1. So the first flip-flop will be in a hold state, the second one in a transparent state. On the contrary, when clock switches to 0, we have that the first flip-flop switches to a transparent state, while the second one switches to an hold state. Now, give a look at the output. Give a look at what happens with the operation of this circuit. Now, consider a clock signal having a duty cycle equal to 50%. At this point, it is not mandatory that it is of the 50%, but in general, in this situation, it is used with a duty cycle equal to 50%. Now, okay, now let me to clean the scheme. Okay, okay, now imagine at this point that, for example, here you have that normally the second flip-flop is in a state where Q is equal to 0 and not Q is equal to 1, but just to fix the idea is just to fix a starting point. Obviously, you could use what initial condition do you want. Now, imagine at this point that I want to store a 1 in this circuit. Okay, so I want at this point that D becomes 1. Okay, now imagine that now clock is 0. Perhaps it's better if we start. Okay, imagine that clock is 0 here. Okay, so we are here at this instant of time. If clock is equal to 0, here we have 1 and here we have 0. Now, by looking at the first flip-flop, if in this situation, what is the value that after a short delay this first Q will assume? For example, we could name this signal like a P, just to give it a name. What is the value that P will assume after a short delay, depending on the circuit that is composing the first flip-flop? Okay, so if D is equal to 1, clock is equal to 0, P becomes 1. Okay, perfect. And now, what about the second flip-flop? What about Q here? What happens to Q and not Q at the output of the second flip-flop? Perfect. Now we have that when clock is equal to 0, the output Q and not Q cannot change. Okay? At this point, you could say, but that was exactly what happens with normal flip-flop. Okay, you are right, but let me to continue. Now, imagine at this point, on the contrary, imagine that on the contrary, clock is equal to 1. So, please reset this situation and imagine that clock is equal to 1. So imagine that we are now in the interval of time. So clock is equal to 1. Obviously, we have 1 to the second flip-flop, 0 at the input of the first flip-flop. Okay? Now, what happens to P? If D change, D switches to 1, what happens now to P? Nothing. Nothing, because this is in hold state. So P continues to be the previous value, the value that P had before the change of D. And now, obviously, if P doesn't change, we have that the second flip-flop now is transparent, because the input clock now is equal to 1. But if P doesn't change, because it is constant thanks to the first flip-flop here, if P doesn't change, then nor Q, neither not Q, will change. Okay, is clear to you?
Yes.
So, in the semi-period where clock is equal to 0, the output can't change. Can't change because the second flip-flop is in hold. And the new value of P cannot pass through the second flip-flop. When the clock is high, then Q cannot change. The output at Q and not Q obviously cannot change, because we have this time that the first flip-flop is in hold. It so maintains P constant, and Q and not Q cannot change. And now it is a very great difference with respect to the operation of a single flip-flop. So now we have no more an interval of time where this circuit that globally these two flip-flop placed arranged in this way, there is no more an interval of time where both flip-flop are together transparent. But at this point, when I could change the value, that is when I could change Q and not Q, at this point there is just one instant of time when it is possible, and in particular let me to check. Oh no, here we had 0 and 1. Okay, now what you have to consider now? Consider a first interval where clock is equal to 0. Okay, clock is initially equal to 0. Here is equal to 1. Here is equal to 0. Now, during this first semi-period, the first one is transparent, the second one is in hold. Okay, but if the first one isn't transparent, P could change, and indeed it changes to switching to 1. Okay, now at this point the clock goes high. We are at this instant on time here, exactly here. And what happened? Happens that clock switches to 1. This signal switches to 0. This one obviously switches to 1. That means that the first flip-flop goes in an hold state. Okay, so P cannot change anymore. But the second flip-flop switches to a transparent state. So the value of P now can be written. The second one is transparent, so the new value of P can be written. And at this point, Q switches to 1 and not Q switches to 0. That is, yes?
May I ask a question? Sorry, Professor. Can we say that the circuit is holding the P value for a period and then releasing it to change the Q and not Q?
Yes, in the second, not in all the period, in a semi-period.
Semi-period, yes.
Semi-period, okay. Now, but your interpretation, I don't know if your interpretation is completely correct, because now what happens? It is true that P now has been released to Q and not Q, but the change of the outputs happen only at this time, at this instant of time. The output cannot be changed in this interval, cannot be changed in this other interval, in this semi-period, and nor in this other semi-period. But the output can change only in this interval, because in the first semi-period here, we at most can change P. Then in the second semi-period here, we have that the value of that P as assumed during the first semi-period can be released to the output. But since the first latch here, the first flip-flop here is in hold, P cannot be changed during this semi-period. So in the first semi-period, Q and not Q cannot change, because D has no effect on P and on Q and not Q. In the second semi-period, the output cannot change because P has no effect on Q and not Q. The only instant of time when I can change the output is this one, is when the clock goes high. When the clock goes down here, nothing changes, because when the clock let me to clean here. Imagine now, for example, that clock comes back to 0. 0, 1, and then once again 0. So we are, for example, here. Okay. And now what happens? Now happens that the second flip-flop comes back in an hold state. The first flip-flop comes back in a transparent state. It was transparent, hold. it becomes another time transparent. So what happens? It happens that at most the value of P could eventually change if D has changed, but not Q and not Q. They cannot change when the clock goes from high to low. Okay, so what happens is, as I said, just to repeat, is that the output Q and not Q can be changed just in one instant of time. This one. Here, 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 and so on. So the output can change just one time for each period. If this is the period of the signal, we have that the output can change only one time here in one period, one time here, and so on. At this point, if you imagine that this arrangement, so these two flip-flop connected in series with these inverters, we can use here a box that embeds both the flip-flop, and so we can use a new symbol to indicate that this is a D, Q, not Q, and clock. Now, we can substitute this new circuit here, this one, in the example that I made before. Here, we can substitute this one, and this other one. At this point, all of your problems have been solved, because now we have that A first, B first, C first, and obviously even Y first can change only one time in a period. So I applied a clock signal that is shaped like this square wave with a duty cycle of 50% equal to 50%, and we have just one change of A first, B first, and C first here, then here, then here, and once again. So at any change of the inputs A first, B first, and C first, we can have just one change of Y first, but Y first can be stored in the last flip-flop just one time for each period, when the clock from low goes high. And at this point, you can see that we have effectively a periodicity in the elaboration, because we have no more a semi-period of the clock where the circuit can operate completely as a combinatorial circuit. We have no more transparent state. Okay?
Okay.
Is it okay for all of you?
Yes.
Yes.
Okay. since it is a very critical step, I suggest to make a simulation, but it must be okay. I need to give you another circuit topology to show how to implement this flip-flop in a more compact way, because now this flip-flop is composed by two D flip-flop connected in series. I want to show you a more compact implementation. However, it is important now that regardless that if it is a master-slave configuration, obviously this is called a master-slave configuration because the first flip-flop behaves like a master, and the second one like a slave. This is because if, namely, the second flip-flop is capable to store only the values that are imposed in P, but values of P are imposed by the master flip-flop. Okay, so conventionally, this structure is called like a master-slave configuration. Okay. Now, I want to show you a simulation. I don't want only to show you. I want that we could make a simulation together. Okay? By using these. Okay? Now, okay. I want to show you how to use this flip-flop with these. Now, let me to interrupt this key. Okay. Okay. Now I'm sharing the lead simulator. Can you see it?
The simulator ahora. Yes.
What? Yes.
Yes, the simulator. Okay. Now, these flip-flops are present here. Okay. In particular, we have just to better understand. Now, the symbol here. Now, flip-flop D, flip-flop E, flip-flop JK. They are flip-flop with the enable. Let me to. Sorry. Now, PET here is the acronym of positive edge triggered. I forgot to give you the terminology. Since now we have a master-slave configuration that globally behaves like a flip-flop, just to distinguish this from the previous one, from the flip-flop that can be old and transparent, we say that this new flip-flop is edge triggered. Okay, namely it is triggered on the edge of the clock. Okay. In particular, since we we have that the output Q and not Q in the example that I made before can change only when the clock goes from low to high value. So only when the flip-flop is switching from low to high, we say that it is a positive edge triggered. That means that we have a flip-flop that can store a value, can change the output only at the edge of the clock, and in particular only at the positive edge. The acronym is PET. So we call it, like for example in the case of the D, we call it a D PET flip-flop. Okay? Is it okay for you?
Yes.
Yeah.
Okay. This other terminology, NET, is for negative edge triggered. That means that we have an edge triggered circuit. So we have, in that case, a master slave. But in this case, the output changes only on the negative edge. So when the clock goes from an high value to a low value. To implement a negative edge triggered flip-flop, you have simply to change the position of the knot that we used to invert the clock signal. If you apply the knot at the second flip-flop and not at the first, you will have a negative edge triggered. We can simulate this in order to understand the behavior. Now, here you have, in these components, you have these flip-flop that are positive edge triggered. You have here an RS flip-flop that is not a clocked one. You can see here that you have not an enable nor an enable, neither a clock signal. This is a standard latch. And here you have negative edge triggered flip-flops. And here you have latch that are that can be hold, that can be transparent and old. This flip-flop here, to evidence the difference with the negative and positive edge triggered, they are called level sensitive, since they do not operate only on the edge of the clock, but they are sensible to the level, to the fact that the clock can be 1 or the clock can be 0. Okay, so they can be transparent. So when they are transparent when the clock is equal to 1, so they are sensible to the level, to the constant value of the clock, not to the switching, not to the edge of the clock. Now, look for example at the operations of these. Okay. Of this one. Now here we have an enable, a preset, and declare that are active low, Q not Q, S and R. I want to use a D. It is much more easy to understand. Now, first of all, I want to disable preset and clear, so they must be put both at 1, at a constant value, So I want to put this high level constant value here, and by using wires I want to connect this one, and I want to connect this one. In this way, preset and clear do not operate. Now, I want to generate a periodic signal to use in the enable. Then I need to use another component, another input component that here is indicated like clock generator. Okay, I want to put it here. I don't know if you can see this small window that is opened.
Yes, we can see.
Okay, perfect. Now you can use a label for this periodic signal. Obviously, we can call it clock. CLK is usually the abbreviation for clock. CLK is used. Here you can set the initial value that could be low or high, but it is a periodic signal, so it is not important to establish before what is the initial value. Much more important is the clock period that determines the speed at which we produces the output. In a simple circuit, it determines the throughputs of the circuit, namely how many data I produce in the interval of time. And here, as you can see, we can change the frequency of the output, starting from 1 Hertz up to 1 gigahertz. Now, we can use the value that the default value that at this point is not so important. I don't remember. Okay, this one, 5 megahertz. Perfect. Okay, now obviously we have to connect this clock here at the enable input. We have to monitor Q and not Q, so we have to add these outputs components, one here. I suggest to use the same label of the name, so Q and not Q. You can indicate not Q by writing here Q and using this box neg. Okay, you can see here that appear not Q. Using wires, we have to connect these two ports here and here. Then we have to add another input that is the effective input of the circuit, so the input switch here. We can call it D. Okay. So the circuit is finished. I suggest to make these operations with me. You have to save the circuit. It is a level sensitive D. Okay. We have just to simulate it. This point. You can see that when this waveform viewer, this window opens, you already have the clock that is switching. Okay. At this point, we have to change the value of D, and imagine that let me to make a zoom. Okay. Now we have that D, for example, can change here when the clock is high, then can change here when the clock is low, then can change another time here and here, and at this point all the instant on times are equivalent. Now we have to place the end time cursor to stop the simulation here and play. Okay, now what happens? Here you have at the beginning here you can see this strange waveform that does not represent a 0 or a 1. This is because the system does not know what is the actual value, because the clock has never changed from the initial instant of the simulation, and so the output are undefined. They are defined only when after that the clock goes high for the first time, because only when the clock goes high for the first time we have that the output is connected to the input and the output is determinate. Okay? When the clock is low, in this semi-period here, let me to make a zoom. Okay, in this semi-period here, the flip-flop is in hold, so the output cannot change with respect to its previous value. But what is its previous value? We don't know. The system doesn't know, and so here we can see these two strange waveforms that are undeterminate. Now, when the clock here goes high, okay, here you can see that the output changes, and suddenly after a bit delay we have that Q becomes 0 and not Q becomes 1. So it means that when clock is high, the output has taken the same value of the input D. Now take a look here at this instant of time. We have that once again. Okay, here once again we have that the clock is high, so the flip-flop is transparent. We have that when D changes here, the output sorry, well, the input changes, the output change. Both the output change. And I suggest to note that here we have that the output change during the same semi-period when the clock is high. That means that the flip-flop is level sensitive flip-flop. Here in this interval of time it is transparent. And then I suggest to note that there is a bit delay between the changing of the instant on time where D is changing and when Q and not Q are changing. This delay is a normal delay and is due to the delays of the logic gates that compose the flip-flop. Now, if we proceed with the simulation, if we look now at this instant on time here, then you can see Here D is changing, D goes low. But since the clock is low, namely the flip-flop is in an old state, the output don't change. Q remains at 1 and not Q remains at 0. The output change only when the flip-flop becomes transparent, here when the clock goes high. After that the clock is high, we have the change on both the outputs. So this is a typical behavior of a level-sensitive flip-flop. Another example here, you see that D goes high, but the outputs don't change. And once again, they change only after that the clock is high. Okay, is it clear to you, simulation?
Yes.
Now, I want to show what happens if we build a master-slave flip-flop. Okay, we have to put another level-sensitive flip-flop. We have D. We can connect the preset and set here and here. Okay. Now, the output Q and not Q must be connected here, one here and the other one here. Okay. Now I suggest to look at these two signals. Sorry, we can make this. Okay. Oops. 1 and 1. Okay. I suggest to change the name of these two outputs, and in particular, if you want to use the same notation that I used before, we have to call these, to name these as P, and obviously here we have not P. Okay. It is convenient to explore also the variations of the intermediate signals P and not P. Even if they are not actual outputs, it is convenient to analyze the circuit. Now, if we want a positive edge triggered flip-flop, a PET, PET, we have to add here a NOT, like in the discussion that I showed before. If we want a negative edge triggered, we have to add the NOT here at the input of the clock of the second flip-flop. Now, the first time, I suggest to use the same scheme that we used during the discussion. So here we have a NOT, this wire, okay, now at this point the scheme is ended. We have to simulate it, but are you plotting the scheme with me?
No, actually, it's a little bit fast for me.
Oh, and for all of you? Am I too much faster?
I was looking and doing it on a paper. Then I will try on PC.
Yes,
okay. Okay. So to simulate here, obviously, I always suggest to make an error checking here. Let's see. So we have no errors. Timing simulation here, perfect. Okay, zoom. Okay. Now we have that D, for example, can change here. So D becomes 1 when the clock is high. Then we can change another time D when the clock is low. No, sorry, here is high. Okay, here is low. We can change it another time when clock is low. Then when clock is high, and so on. Okay. Simulation up this instant. Then, okay, we can go to simulate. Okay, now we have firstly look at the Q and not Q. We can expand these signals here and here. Okay. However, it's not important this. Now, first of all, as I said, we have to look at Q and not Q, but in particular they are complementary, so we can look at Q. You say that Q is undetermined here. It assumes a value only after that clock is going high. P and not P, the intermediate values become asserted much more in a lower time, because I want to look at the scheme. I want to remember that when the clock is low, the signal here is high. So this first flip-flop, level sensitive flip-flop, is transparent. That means that the output P and not P suddenly assumes a determined value, determined on the value of D, and indeed this B here is equal to 0. because, as I said, latch initially is transparent. Obviously, if the clock starts with the value 1, we have on the contrary that this P and not P will be defined after a semi-period of the clock. On the contrary, Q and not Q are undefined up to the first positive edge of the clock, because up to this point, this second level sensitive flip-flop is in old state. Okay, so the output are not determined. Now, after this observation, you can see here at this instant we have that D goes high, both the outputs don't change. Here we have that the clock here goes low and the output Q and not Q don't change. After a while you have that P and not P change, but it depends on the master-slave behavior of the circuit. The important thing is that Q and not Q remain constant. We can see here that D changes when the clock is low, and once again the output don't change. You can see that the outputs Q and Q never change. They change just here after this edge here, because here D is high, the previous value of Q and of Q is equal to 0. So when the clock goes high at this instant, the output switches to the same value of D. And this is the only instant of time where Q and not Q change. You can see that, for example, the outputs doesn't change here, doesn't change here, and so on. Okay.
Okay.
This is clear to you? So, in order to store a new value in this master-slave flip-flop, we need to put the input value of D, the value that we want to store into this master-slave flip-flop, and then we have to wait that the clock goes high. When the clock goes high, the value of D is acquired, is sampled by the flip-flop, and then D is free to change another time. If we save this configuration, store as test sequence, okay, close, yes, I want to save. I want just to change the position of this inverter here. Okay, Now we have moved the inverter on the second flip-flop. Say launch again simulation, load test sequence. Okay. If I launch the simulation, we see that the behavior now is a negative edge triggered. So the output Q and Q change only after that at the instant on time where the clock goes from an high value to a low value. And indeed, for example, it changes here. We have, for example, Q and Q that are 0 and 1, but now D here is 1. When the clock goes low here, the outputs change. Okay. Here, for example, D goes another time low, but the output remains constant. The output change only after that the clock has gone low. Okay, so it is a negative edge triggered flip-flop in a master-slave configuration. If you want to use a edge triggered, however, you could eventually use this component that already exists. For example, this circuit behaves like this one. You can see that here you have a negative edge triggered. You can see the negative behavior by the presence of this bubble here at the input of the clock. A bubble that is not present here for a positive edge triggered. Okay, the difference between these two symbols is only in this bubble that represents the 0 or the 1, the positive or the negative edge behavior. Okay. At this point, if you have no questions, I think that the lesson, we can end the lesson here. They are almost 10 to 5, so it's time to end the lesson. If you have any question, I will give you any explanations. On the contrary, we can say goodbye, and we will see you tomorrow.
I have a question. Which chapters of the book we should practice, like 5?
Six, I presume. Six. Let me check.
5, 6, and 7.
Five.
5, just 5.
5, yes.
Okay, thank you.
All the circuital implementation of the flip-flop, latches and flip-flop are in the 5th chapter. Because then in the next chapter we will see this synchronous network. We will use this flip-flop to implement some more complex structures like FIFO registers, SIPO registers, shift registers in general, so common circuital construct based on the flip-flops.
Okay.
And in the last theory chapter, the 7th chapter, we will see how to use this structure to build finished machines, to build control circuits. The 8th chapter are essentially applications, are examples, exercise that we can make together. Okay, so you have to study the 5th chapter.
Okay.
Okay. Goodbye. See you tomorrow.
Goodbye. See you.
Bye.